let's go ahead and get started. So a couple of announcements. So don't forget we're in week 8, we're in week 9 now. So week 9, so we have 2 more weeks of lecture, and then finals week. So the plan for week 11, if you haven't looked ahead, so we have 2 exams. So we'll have a lab practicum, and this should be available online probably at the end of week 10. And so everyone is going to do the lab practicum online. So even if you're doing the lab in person, just to make it fair, the lab practicum will be online for everybody. And so you'll have, that whole exam week to do it. So it'll be officially due, I think it's June 17th is the last day of quarter officially. Yeah, I think that's a Friday. Sorry, I need to glance at the calendar. Yeah, so June 17th is that Friday, so that's the absolute last day it's due. And then, so kind of brainstorming about the exam still. So right now I'm thinking that we'll do the in-person exam on Thursday, and that's only because I assume everyone wants a review on Tuesday. So test Thursday. And so as of right now, I'm also planning it on just making it available online that Thursday as well. So again, you would have like a 24-hour window to complete the exam. And if that Thursday doesn't work for you, then we can try to make different arrangements. So any questions about that? Just logistics to bring us to the end. All right, so this chapter is pretty important. So I think it's like probably the next most important thing that chemists do is make solutions, like the stockroom, for example. That's all they're doing in there most days. It's either they're calculating moles or they're making solutions for us. So let's dive in how we would do that. And so I'm sure you all have done this before. Mix some table salt in with water, and then it just seems, to disappear. And so we've defined this before as a homogeneous mixture. And so we know the salt's still there, right? We could taste it, and it would taste salty, or we could, of course, boil away the water, and salt would be left behind. And so just kind of our definition here, so that means a homogeneous mixture can also be called a solution. And then the minor component, so basically what is being dissolved, is the solute. And then the major component is called the solvent. So usually, the liquid part doing the dissolving. And so you've probably seen different mixtures around in your life. So there's a special class called colloidal mixtures. And so the particles in a colloid are large enough to scatter light. And this gives us a phenomenon called the Tyndall effect. And this can make colloidal mixtures appear cloudy or opaque. So this is just a colloidal dispersion of gold in water. But you're probably familiar with a bunch of other types of colloidal mixtures. So for example, you could have liquid aerosols, like when you get fog or mist. So you know how if it's foggy, right, that light kind of scatters about, and it's hard to tell, like when it's foggy, where the direction of light is coming from. So that would be an example of the Tyndall effect. And for gases, so that would also be dust and smoke. So again, if you smoke or if you see like dust, you smack your couches in the light and a bunch of dust appears and you can see it. That's again that same effect. And then so other examples would be like whipped cream, shaving cream. So that would be a liquid gas system. You could also have paint, so water-based paints, milk, mayonnaise, detergents. You can have liquid solids, so that's going to be gold in water or oil-based paints. Solid and gas. So if you've seen a pumice stone, it has those little air holes in it. So that would be another example. Same with styrofoam. And then for solid liquid, you could also have cheese or gelatin. All those give you the Tyndall effect. You know, think of like your Jell-O. Or solid. So this would be considered like different colored gemstones, all those little impurities in there giving it the color. So ruby glass. So now let's look at different solutions and solubilities. So now we're going to be comparing, so what's the difference between salt and sugar water? And so we have this little saying, so like dissolves like, and we'll dive into this more. But basically you want to think back to last chapter as well with your intermolecular forces. And so if we look at what happens when a solute dissolves, so of course there are attractive particles, forces, holding the solute particles together. So this would be, right, your sodium chloride or whatever that's here. And then there's also attractive forces between the solvent and the molecule. So then you're kind of asking yourself, well, is the solvent-solute interaction enough then to overcome this solute-solute interaction and then, of course, solubilize whatever you were trying to dissolve? And so if the attractions then between the solute and the solvent are strong enough, then of course you'll notice your solute dissolving. And so now we're going to revisit water. So we already know that water is polar. We also mentioned that water has that additional hydrogen bonding effect. And so we mentioned, right, oxygen has our negative electron density. It's very electronegative, so it's also kind of stripping hydrogen of its electron density, so giving us this electron distribution map here. And so when you have a salt then, like sodium chloride, so we mentioned that all, right, the interactions are electrostatic. So now we have our electrostatic interactions here. So of course, we're thinking, is this solute-solute interaction, so our sodium cation and our chlorine anion, is that strong enough to overcome this solvent-solute interaction, or will it dissolve? Oops, sorry. And so what you find, too, is, of course, they do dissolve in water. And if you look at how they interact, so this is why polarity matters here. So we have our negative end of water pointing towards our sodium here, so negative attracting our positive, and that means chlorine is an attractive to the positive end with the hydrogens. So there you have those interactions. And so each ion then is attracted to the surrounding water molecules and pulled off and away from the crystals. So now we can imagine, right, a large block of sodium chloride, and then as these water molecules come along, they start plugging off, right, the ions. And so when it enters solution, the ion is then surrounded by water molecules, insulating it from other ions. So there again, we have our sodium chloride solubilizing. There's our sodium cation. And of course, you can see how it's surrounded by waters, and all the oxygen ends are pointing towards it, compared to the chlorine, where all, again, the positive hydrogen ends are pointing towards it. And so this results in a solution with freely moving charged particles able to conduct electricity. So do you remember that from that lab with the light bulb test? And so that's why, you know, that light bulb, so thinking back to that lab, it didn't light up in a bunch of sodium chloride, right? Because there's no movement, so it's just a solid bunch of sodium chloride. It didn't conduct electricity in just plain water, since we don't have any ions moving around. But then once we had our salt in solution, now we have our ions freely moving about, and that's when we can conduct electricity. And so this means that materials that dissolve in water to form a solution that will conduct electricity are called electrolytes. And so an electrolyte has to be then some sort of ionic compound that's going to disassociate in solution. And some materials that dissolve in water to form a solution that will not conduct electricity are then going to be non-electrolytes. And so to compare, that would be sugar. So sugar is a covalent compound. So if you put it in water, right, it's not going to separate, it's not going to do anything. But if it's not separating into ions, then that also means it will not conduct electricity. So for any non-electrolytes, this would be covalent compounds. And so now kind of comparing salt versus sugar in solution. So again, we have these really strong interactions. So these ion interactions are extremely strong, so we get that dissolution. And now looking at sugar, so here's our sucrose molecule. So it still kind of has, right, oxygens and hydrogens. And so we still have some interactions. So you can see that, right, the water molecule, again, the oxygens are going to be attracted to the hydrogens or any partial positives on the hydrogens versus the water molecule being attracted to like the negative parts. So for example, this oxygen, right, the water is going to orient the hydrogen towards that. And so it still is dissolved, right? And we can think of, okay, well, there's polar interactions. And so these are both kind of polar of sugar and water. So then it at least dissolves in solution. So then we can classify them by how they dissolve in water. So a strong electrolyte is again going to completely disassociate. So again, this is ionic compounds or strong acids and bases that completely disassociate. So we have an ionic compound. Here is one example, so calcium chloride, and then it would make one equivalent of calcium and then two equivalents of the chloride ions. So other kind of strong electrolytes, that would be HCl, so that also completely disassociates, or nitric acid, so that's another strong acid, and so that also would completely disassociate. And then so weak electrolytes then only have partial disassociation. So this is going to tend to be these weak acids, are a lot of examples. And so we have, looks like formic acid here, and so it's just losing this H to make the conjugate base of A, so this is HA, disassociates into H plus and A, and I don't like how they drew that arrow. So this should be an equilibrium arrow like that, not this. They probably couldn't make that on the computer. But it should be this kind of equilibrium arrow. So again, showing that you have partial disassociation, so equilibrium going back and forth. And that means that this H plus can react with the conjugate base and reform the acid. And then again, it mentions that compounds that do dissolve in water but do not form ions are called non-electrolytes. So then if you have this strong electrolyte, like sodium chloride, or again our strong acid, then that means we could put the light bulb in and it would light up really bright. And then here's another classic example of a weak acid, so acetic acid. So this is what vinegar is made out of, is a weak acid. So it partially disassociates. And so you have your acetic acid, and so that means in solution, it's again going back and forth between our acetic acid and then our acetate ion. And so weak electrolyte, if we were to stick a little light bulb in it, it would probably just light up, partially or not as strong as the HCl. So of course this would be a function of how disassociated it is and how strong of a concentration your weak acid is. And so this means, right, sugar is a molecular compound, aka covalent compound. And so most molecular compounds, except for acids and bases, and of course ionic compounds, dissolve in water as intact molecules. So again, just keep thinking back to those covalent compounds. And again, that makes our non-electrolyte solution, so it's not being deprotonated or anything, not disassociating, so it's just our non-electrolyte sugars floating around in water.
Where is everyone?
So here's our little light bulb demonstration, just kind of as a recap. So again, if you were to do sugar in water for our non-electrolyte solution, the light bulb would not light up. If we move over to acetic acid, so you can see, right, it has a very faint glow since only a small number of ions are liberal in solution. And then, so just compare that from going acetic acid to sodium chloride, how much brighter that light bulb is, so now full disassociation and ions floating freely. And so now we're going to kind of throw a wrench into this for a second. So the solubility of ionic compounds. So not all ionic compounds dissolve in water. And you probably have kind of gotten a sense for this in lab. So sometimes you mix two things together and then you start getting a precipitate. And so one example of this is silver chloride. So you can add a bunch of silver chloride to water, and then it would just kind of sit there as a white powder looking at you.
So basically the max saturation for silver chloride dissolved in the water is 0.
Not 0, but we won't go there.
Also, a tiny amount gets dissolved technically, like trace amounts?
Yeah, so that's like beyond the scope of this course.
Okay, so it's not that it's completely insoluble for the most part, it's just that it's so low that it doesn't particularly matter?
Yeah, and so there's a couple of things for this. So you can always, if you're bored, so if you want a definitive answer on how much goes into solution, Wikipedia usually has a solubility. And so you'd probably be interested in this number because this would probably make the most sense to you.
Yeah.
So 520 micrograms per 100 grams of water, and that's at 50 degrees Celsius. Unfortunately, they report the solubilities at like different conditions and different amounts, which is kind of annoying, but whatever.
It wouldn't be science if you didn't have to course through the data yourself. Calculations.
That's true. And then, so what I was kind of talking about beyond the scope of this course, you would use this KSP and do some math and blah, 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 and figure out exact concentrations. But again, we don't really care about that right now.
Water has 100% solubility in water.
Yeah, I don't know what they put for that. Probably NA. And so in general, if we have this kind of insoluble compound, then we say it's insoluble, versus if a compound is soluble, then we say it's soluble. And so I'll probably print out some more rules for you. I'm sorry, I ran out of time. I forgot you might want that. So now the question is, well, how do we know, right? So we can put silver nitrate in solution, and this forms a strong electrolyte. And maybe you've seen it, right? In lab, you've worked with the dropper bottles of silver nitrate, pretty common. So why is silver nitrate soluble while silver chloride is not? And so unfortunately, right, there's no easy answer. There's a couple of solubility rules. Obviously, the best way is to do experiments and so forth. But we do have kind of these general guidelines. And so the other thing is, so you may find a few small discrepancies here and there, especially if you look at other solubility charts. So I'll kind of point that out where they occur. So let's look at the most simplest rule and the first rule here. And so we have the top portion of this chart, compounds are generally soluble. And so that's going to be lithium, sodium, potassium, and ammonium salts are all soluble, and no exceptions listed. And on an exam, you would have to have this chart. I don't expect you to memorize it. And then so nitrates and acetate ions are also almost always soluble. And so now this makes sense. Okay, well, that's why silver nitrate is soluble. We have this rule here. Yeah.
Wait, you said almost always, so I'm guessing there's an exception that's just not listed because it's too niche, or?
Yeah, I mean, I don't want to say always because there's probably some exception somewhere.
So exception none that we'll encounter, I guess.
Pretty much. I'm trying to. Yeah, apparently bismuth oxynitrate is insoluble.
Yeah, that tracks. That seems the weirdly amount specific enough.
But yeah, for the most part, nitrates, we assume they're soluble. And then, so now here start to come a few exceptions. So chlorides, bromides, and iodides. So those are usually soluble, except when they're paired with silver, mercury, or lead. And then those will be insoluble. And then sulfates, so those are another one. These are generally soluble, and this is also where the trouble arises. So when sulfate is paired with strontium, barium, lead, silver, or calcium, the resulting compound is insoluble. But sometimes, like barium and especially calcium sulfate, that one's kind of on the edge of solubility. And I would have to pull up like a specific scenario, but sometimes if you have like two competing, I guess, questions, because these work with double displacement reactions, the precipitation is what drives it forward. But then sometimes you may be kind of given a scenario where it wants you to think calcium sulfate is soluble, but that would make more sense once we encounter it. And so you can see too, if you look at Wikipedia, so its solubility in water is like 0.26 grams per 100 milliliter. So it's not a crazy, unreasonable amount, but it is, again, fairly small.
And it's at 25 degrees Celsius. Great. That's fun. So what counts? Like, what's the threshold for it being counted as soluble?
I think that really is, do you mix two things together and then do you see a precipitate? I'm sure there's probably like a better answer,
I'm more
but
about like, is it like, because like there's different degrees of solubility. Like, is there a range you know of, or just not really? It's more of a try it and see what happens kind of thing.
Yeah, I mean, so for us, right, we're taking a try it and see what happens approach, right? Because
Got it.
again, what we're interested in is if we mix two solutions together and we get a precipitate, what is that precipitate? So this is kind of like our answer bank. But if you were doing, some sort of quantitative analysis, then you'd have to look into the KSP and actually do, more in-depth calculations. So again, this is like a really
Got it.
broad overview. And then, so now let's look at the ones that are generally insoluble. So usually hydroxides and sulfides are insoluble, except when they're paired with lithium, sodium, potassium, or ammonium. And so these are also awkward exceptions. So when sulfide pairs with calcium, strontium, or barium, now it's soluble. So note that. And hydroxide, this is another one that is on that edge. So you might see it referred to as solid or insoluble. But calcium hydroxide, strontium hydroxide, and barium hydroxide are all considered, again, slightly soluble. And then, so carbonates and phosphates are also generally insoluble unless they're, again, with lithium, sodium, potassium, or ammonium. So hopefully you're seeing a little bit of a pattern there. And then, so solubility, just to compare, of calcium hydroxide. So it's 1.89 grams per liter. And, I mean, what's kind of funny is these rules don't even really, they're not consistent with each other. So if you just look at the math, calcium sulfate, we said that's insoluble, but its KSP is 10 to the negative 5 versus calcium hydroxide, which is negative 6. So technically, calcium sulfate is more soluble. So again, that's why I kind of consider these rules a very helpful guideline in determining our problem, but not always hard and fast rules. And so that's also why you may find, again, little discrepancies in what's soluble, what's insoluble, especially for these calcium and barium ones. All right, so let's see if we can predict. And again, just go off the rules here. So we'll give everyone a few minutes to look at that. So predict whether each compound is soluble or insoluble. So we have lead chloride, copper chloride, calcium nitrate, and barium sulfate. So again, everyone take a few minutes and then we'll go over them. let's see what we got. So what do we think for the first one, lead chloride? So insoluble, exactly. So that was one of our exceptions. So, okay, chloride usually soluble, but okay, lead is insoluble. Good. What about the next one? Copper chloride. I see chat also said insoluble for lead. What do we get for copper?
I said it was soluble.
So exactly, so soluble. So we go up, again it's another chloride salt, not part of the exceptions. And I see it in the chat as well, soluble. Excellent. What about calcium nitrate? So I see soluble in the chat. Awesome. So soluble. So that's one of our nitrates. So again, no exceptions, at least not any common ones. Calcium nitrate, soluble. And then last one, so barium sulfate, soluble, insoluble. Insoluble, I like it. So where's our sulfate? There it is. And then, all these exceptions, so of course barium is on there. And I see it in the chat as well, insoluble. Yeah, this should be in the book, but in lab I'll print some solubility rules out for you to have, and then I'll have them on Thursday as well. But you could also, Google it. You can find tons of charts online, and they should, again, I'll say relatively the same thing, but if you find, a little discrepancy, don't freak out.
Don't freak out, panic.
Definitely not.
Science is never wrong. That's why it's science.
All right, so let's look at this temperature dependence of solubility. So you probably know this, but in general, so solubility increases as we increase the temperature. So solubility is generally given in grams of solute that will dissolve in 100 grams of water. Of course, like you saw in Wikipedia, it's not always that nice, easy of a number. And so again, for most solids, the solubility of a solid increases as the temperature increases, and you would expect that. So of course, more movement, you get things dissolved. And so there are a few exceptions, such as this cerium sulfate compound. So I don't have an exact explanation. It's just something about those solute-solute interactions must get stronger at higher temperature versus that solute-solvent interaction. And a lot of that just depends on like ion size, how it's packed in there. So the base,
like how ice gets less dense.
yeah.
In terms of like the exception, not the standard.
Exactly. So again, few exceptions, most have increasing solubility with solids. And again, you probably all know that, right? You're trying to get some sugar to dissolve or something. You probably want to heat it up, increase its solubility. And so we can also look at these different definitions. So these solubility curves can also be used to predict whether a particular amount of solute dissolved in water is saturated. So if it's saturated, that means it has the maximum amount, and you would be right on this curve here. If it's unsaturated, that means we could put more solute in, dissolve more stuff. And so it'd be somewhere, below this line. And then if it's supersaturated, so we'll make a supersaturated solution in lab. But that means we heated it up really hot, stuffed a lot of material in there, and then we can cool it back down. So you probably can't get any more in there. And if you do try to add more, you may get crystallization or something. So this is how you crystallize stuff out. Also really important. And so we just said that solids, again, have increasing solubility as we increase the temperature. And now, put a little star here. So gases, opposite of solids. So now it's the opposite. So if we heat up the temperature, that means that we have decreasing solubility versus our cold soda pop. So we can see this if we're pouring it out. So pouring out our cold soda pop, so our CO2 is still dissolved in there at cold temperatures, so you're not seeing a lot of bubbles. Versus if you have warm soda, pour it out at room temperature, then you would have a lot more fizzing as that CO2 gas escapes, once you bust this seal there. And then so for all gases, the solubility of gas decreases as the temperature increases. And so this is because the delta H of solution is exothermic, since you do not need to overcome solute-solute interactions, right? They're already gas molecules kind of floating around and not interacting. They're also going to be nonpolar, so again, that kind of reduces their solute-solute interactions. And so how do we make a solvent hold more solute? We can vary the temperature or pressure. And so usually as a chemist, you'd be altering the temperature. And so usually you want to try to purify your reaction by selective crystallization. So we can make our solution really saturated or supersaturated by changing the temperature. Again, usually increasing our temperature, or we could increase our pressure, get more solubilized. And then some solutes, instead of coming out of solution when conditions change, get stuck, and then it becomes supersaturated, just again meaning we can put more in than we expect. And so these supersaturated solutions are also unstable and lose all the solute when disturbed. And so example, right, you shake a carbonated beverage and then it fizzes more since you, again, disturbed that saturated solution. And so same thing with crystallization. So you have a supersaturated solution, and then maybe you can scratch the glass or add a little seed crystal, and that'll cause the whole solution to kind of crystallize out. And so let's look at this pressure dependence on the solubility of gases. So the larger the partial pressure of a gas, then the more soluble the gas is. So that kind of makes more sense, right? We pressurize something, and then we can kind of force a bunch of gas molecules in there. And so the solubility of a gas is directly proportional to its partial pressure at that temperature. And then every gas has what's called this Henry's law constant, so Kh. So you would have to, look it up or be given this Kh. But then you can see, so for CO2, if you want to make some soda, so your Kh for CO2 at 25 degrees Celsius will be 3.1 times 10 to the negative 2. And so notice we haven't quite gotten here. We're almost there though. But this is molarity per ATM. And so molarity, again, we're just about to get to. That's moles over liters. You can use your dimensional analysis to help you. And so let's just say what is the solubility of CO2 at 3.22 atm. So see if you can figure out, just with dimensional analysis, how you would get this answer, and then we'll go over it. Here we get an answer. So we have S gas is equal to our KH times our pressure. And so now we can just plug everything in. So you can see we're given, so our KH, 3.4 times 10 to the negative 2, so molarity for ATM. Then we're going to multiply it by our pressure, which makes sense. And so ATM will cancel out, leaving us with units of molarity, which is a measure of concentration. And so let's see, what do we get in our calculator? I'm going to pull up the calculator. So 3.4 times 10 to the negative 2 times 3.22, and so that should give us a molar solubility 0.109, or let's see, we'll round it to 3 sig figs, so 0.110 molarity. So does that make sense, how to approach those? And so again, KH, I would expect it to be given in molarity per ATM, but again, as always, watch your units, make sure that they didn't change something funny on you. So there's different units of concentration. Of course, they could have put in a different pressure too. So just watch all those things. All right, so now we're kind of getting to this concentration thing. And so solutions have variable composition. So to describe a solution, we need to describe their components and their amounts. And we also have these terms kind of dilute and concentrated, which also kind of help us. So dilute, I consider kind of anything less than 3 molar or so is about dilute. And again, these are just kind of rough descriptions. And then concentrated, I would kind of, especially like 6+ molar, but you know, kind of above 3 is concentrated or so. Again, just kind of rough descriptions. And so the concentration then is just some amount of solute in a given amount of solution. All right, so we'll go through all of these one by one. But here's just a quick kind of overview. So these are all the different ways that concentration can be expressed. So we have molarity. This is the most common and probably the most used. So molarity, so that's going to be moles over liters. Molality also comes up. It's a little m, and notice, so it's amount in moles still, but over kilogram of solvent. So that's kind of interesting. And then we can have mole fraction. So we've done mole fraction, if you think back to your pressure chapter, the gases chapter. And so remember, that's just amount in moles over our total amount of moles, and that would be unitless. Then we could change the mole fraction to a percent, just multiplying by 100. Then we could do part by mass, percent by mass, and then we'll look into parts per million, parts per billion, and parts per volume there. All right, so how do we prepare a solution? And so this is, again, what your wonderful stockroom does all day, every day, practically. And so to prepare a solution from a solid, we have to know how much solution and what concentration we need. So let's say we wanted to prepare 50 or 500 milliliters of 5 grams and 100 liters. So this is a gram per volume amount, or this could be a percent weight by volume. So this, you could say that you have a solution that's 5% by mass if you have a 5 gram per 100 milliliter, since the density of water is 1, so that's also 100 grams. And then we want to dissolve the grams of solute in enough solvent to total the total amount of solution. And so there's a reason why they say it that way. And so let's look at kind of how we would prepare this. And so notice we have a special piece of glassware. So this is called a volumetric flask. And so these volumetric flasks are extremely accurate, but only for measuring one volume. So in this case, these are 1 liter volumetrics. So that's all it measures, 1 liter, again, extremely precisely. And so we want to prepare, let's see, so it looks like we want to prepare a 1 molar sodium chloride solution. So that means 1 molar, which is equal to 1 mole per 1 liter. And so that means that we need a mole of sodium chloride. And so that's why they say weigh out a mole. And of course, you can tally up the mass for yourself. So 22.99 plus 35.45 should get you 58.44. So that's our molecular weight. And that's how much sodium chloride we want to add. So then you would add your solid and then add just enough water till it's dissolved. And then you want to swirl it around, mix it up. And then once it's nice and mixed, then you just want to top off the volume to, again, precisely 1 liter. And so to do this, you'd be looking at your volumetric. You have to get down at eye level. And if you go over, you have to start all over again. Yeah.
So does the dissolved amount count towards the volume at all? Like,
So that's why they say to prepare it in this manner. So you would not want to go 1 liter and then try to dump in 1 mole of salt, because it does occupy some volume.
I'm saying, so is it technically not 1 mole over 1 liter exactly? Or because it's not 1 liter of water, or is it?
Well, it's still 1 liter of solution total, so you're still filling
Okay,
it up.
1 mole per 1 liter of solution, not 1 liter of solvent. Got it.
Right.
That makes more sense.
And so to kind of clarify any issues that might cause, that's why we have kind of molality, because then we have amount in moles over an exact mass in kilograms.
Okay.
So you could have little, different answers of molarity versus molality.
Wait, those are molarity, molar. Oh, those are spelled differently. Oh, shoot, they look the same to me for a second.
Yeah,
I see it now. It took you saying them out loud for me to get it.
that's why they confuse people, because you have molarity with an R, and then this is molality with an L. So big M, molarity, little m, molality.
That sounds like someone's trying to make a joke about tomato, tomato, or something, with how subtle the difference is. Molarity, molarity.
So again, we have our molarity. So this is our most common one. So again, it's defined as moles per liter. And so if we have then a sugar solution of 2.0 molarity, that means that 1 liter of solution contains 2 moles of sugar, or 2 liters contains 4 moles, or 0.5 makes 1 mole. And you could do the math. So 0.5, or 1 divided by 0.5, right, that would give you 2 molar. So all of these give you 2 molar. And then so molality is defined as the moles of solute per kilogram. And so like you were concerned about, how much volume does it occupy? So this is why some people prefer molality or think it's more precise, since molality does not vary with temperature, since it's based on masses, not volume. So again, subtle differences. And so our molality, again, little m is equal to moles of solute over kilograms of solvent. So for water, it'll probably give you the same answer, but if your solvent has a density of not 1, then that will start to give you different answers. So we can also measure in parts of solute by parts of solution. And so parts are generally measured in the same units, so either grams and grams, kilograms, pounds, or volume.
Moles? It's never measured in moles at all, or no?
So if it's moles, then it's going to
just
be,
molarity.
or that mole fraction.
Why does it not have a unit? Oh, right, because
They would-
it's unitless stuff,
Yeah, they would cancel.
which means you can do anything with the number and it would still be correct.
So percentage, that's just parts per 100. So if we have a 0.9% solution by mass, that means we have 0.9 grams in 100 grams of solution. Or you could change it to kilograms, so that'd be 0.9 kilograms for every kilogram of solution. And then so parts per million, this is a special kind of solute, or excuse me, unit, as we have now parts of solute in every 1 million parts. So the easiest way to define parts per million is going to be this way. So again, you could just do it parts, 1 part per a million parts, so 1 part over 1 times 10 to the 6 parts, so that's part per million. But the easier way to do it would be to put your solute in milligrams and then your solution in kilograms. So a milligram is times 10 to the negative third, kilogram 10 to the third, And so you get that factor of 1 to the 6 right there. 1 times 10 to the 6. So does that make sense for parts per million? And so similarly, parts per billion is again a part over a billion. So whatever part over 1 times 10 to the 9th. But the easiest way to do billion is do micrograms now over kilograms. So that microgram gives you 10 to the negative 6 factor, kilogram 10 to the 3rd. So then we have this factor of 10 to the 9th there. So then our mole fraction, like we mentioned, is just a fraction of the moles of one component in the total moles of all the components in a solution. And so the total of all your mole fractions, so if you have a few substances in solution, they should total up to 1. And so, for example, if you wanted to know the mole fraction of component A, you would put moles of substance A over your total moles, so in this case, just moles of substance A plus moles of substance B. And so like you all observed, so mole fraction has no units then, since moles would just cancel. And then mole percentage is if we just take this mole fraction, multiply it by 100. So here's another important formula and another kind of important what the stockroom does all day, every day. And so usually, right, you purchase your stock solution of nitric acid or hydrochloric acid, or maybe you have a stock bottle of concentrated reagent. But of course for our lab, right, we only use like 0.1 molar or 1 molar. And so that means they have to do a dilution. And so that's just when a new solution is prepared from a more concentrated solution. And so this is the formula that you need. So this is just C1V1 equals C2V2. So this is the most general of this formula. So C just stands for concentration. And so that could be in any unit in this case, as long as, again, you're consistent between your two units. And then volume, it could be in anything, so usually milliliters or liters, as long as you're consistent between V1 and V2, right? So they both have to be milliliters or they both have to be liters. And so you might also see, as some people will say, well, what about this formula? So you have M1 V1 equals M2 V2. So this is just a more specific formula with molarity plugged in there. And so usually you see this simply, again, because you do molarity most of the time. And so you may see this formula, but again, this is the more general form. And so to make solutions of lower concentrations from these stock solutions, we just have to add more solvent. And so the amount of solute doesn't change, just the volume of solution. And so concentrations and volumes of these stock and new solutions are inversely proportional. All right, so let's see if we can do it. So it says we want to prepare 3 liters of a 0.5 molar calcium chloride solution from a 10 molar stock solution. So I'll give everyone a minute or two to kind of think about that, come up with an answer over how much we're going to have to dilute it by, and we'll go over it. you have an answer?
And isn't the answer right there?
I mean, did you work it out though?
Yeah.
Oh, let's work it out. So what'd you get for your volume?
Of what I need to prepare, you mean? Or the volume one?
Yeah, the volume that we want, right? Because that's what we're
Yeah,
calculating.
3 liters.
So let's go through this, because that's not the answer.
Oh, sorry.
So our V1, it doesn't quite matter who's who, just as long as you pair them correctly. So we want 3 liters of a 0.5 molar solution. So this will be my C1. And then we're starting from a stock solution, so C2. And then we want to know, well, how much volume of this concentrated stock solution do I need to prepare this? And so now we can plug all our numbers in. So 3.00 times 0.5 is equal to 10 times X for our volume. So now let's do that. So 3 times 0.5 divided by 10. So then that gives us 0.15, and that would be liters, since we're in liters here for our volume. So 0.15 liters, or 150 milliliters. And so now let's go over how you'd properly prepare that. So now we know how much of our concentrated solution to get. So we would measure out this 0.15 liters of our stock solution. So do that very precisely. Add that to our volumetric flask. And then what we'll do is we'll dilute it with water until we get to our desired volume of 3 liters. And so same thing, you would need to use volumetric glassware. So this is volumetric glassware. And so this would have to be, right, a 3 liter volumetric to do that properly. So does that make sense? Let's try another practice. So to what volume should you dilute 0.2 liters of a 15 molar NaOH solution to obtain a 3 molar sodium hydroxide solution? Do we have an answer? So let's set up our formula. So C1V1 is equal to C2V2. And so now this is V1, C1, and then C2. So I see an answer in the chat. And so now let's plug this in. So 0.2 times 15 is equal to 3 molar times X here for our volume. And so let's see if Chet had it right, so 0.2 times 15, then divided by 3, and so excellent job, Chet.
That's what I got, but I thought I was missing a step because it was one. I was like, and so is that the answer, or are we missing a step?
Nope, that's the answer.
Well, the step we're missing is to actually mix the solution.
Yep, so then we could take this, dilute it to 1 liter, and that would give us our 3 molar. Let's see. Probably save these two for Thursday. So let's answer homework.
I don't even have kilos.
So I realize your homework doesn't have any double displacement examples. So let's at least do one of those. And so an example problem that you might see would be silver nitrate and sodium bromide are mixed together and a precipitate forms. And so we'll just do one example right now so you get a taste of how you would do these reactions. And so first, it's just kind of putting everything together. So we have silver nitrate, so writing the formula down properly, plus sodium bromide. And then we have to ask ourselves, so this is, and these are always double displacement reactions, at least usually, that drive the solution formation. So you have 2 ionic compounds in solution, you mix them together in some precipitate forms. So then you have to ask yourself, well, what are my 2 possible precipitates? And so those are going to be our new partners, so silver and bromine, and then sodium and nitrate. So it gives us sodium nitrate plus silver bromide. And it's right now everything's balanced. But then we have to see, so out of these 2, which one of these is more insoluble? We can flip back to the chart if we need. So what do you think is our insoluble product? Flip back.
Silver bromide.
So AgBr, silver bromide, so we look, okay, we have our bromines, and then we have one of our exceptions, and then we can double check for sodium nitrate, right? Sodium's soluble, so that looks good. Nitrates are always soluble. And so when we write this, so you would have little AQs here. So that means aqueous solution or homogeneous AQ. And then for our solid, we'd have a little S there. And I know this was on your homework too, where you saw like the down arrow. And so that's all that it meant, that if you have a down arrow, this means you're forming some sort of solid. And then up arrows were for gases. And so let's do just one more. So what if we add aluminum sulfate and ammonium hydroxide? So we'll give everyone a minute or two. So what's our formula for aluminum sulfate? Perfect. And then ammonium hydroxide?
NH4OH.
NH4OH. And then so we could do the same thing. So right now, I'm not too focused on balancing. I just want to know who their partners are. So now we swap. So what's my formula for aluminum hydroxide?
Al parentheses OH3.
Yep. And then what's our other product? So how do we write ammonium sulfate?
Plus so NH4 parentheses 2 SO4.
Looks good. And so at this point, we could balance. Balancing isn't quite the point of this exercise, but at least we should be able to do it. So we have 3, put a 3 there, 6. So I think that works. 2 aluminum, 3 sulfates, 6 ammonium, 6 hydroxide, 6 hydroxide. But what we really care about, so which one is soluble and which one is insoluble? This is our product, aluminum hydroxide or ammonium sulfate. We can flip back to the chart. jump out.
The aluminum, would just be aluminum hydroxide?
Yep.
Yeah, aluminum hydroxide, is insoluble.
So that's what I would expect as well. So we look at our chart. And so notice we have ammonium here. So ammonium is usually soluble, almost always. And we also have sulfate here. And so obviously ammonium wasn't any of our exceptions. So, okay, that looks pretty soluble. So we could put aqueous there. And then we go back, let's check aluminum. So aluminum, so hydroxide compounds are generally insoluble. It's not one of these exceptions. So good choice in aluminum hydroxide. All right, I think that's all the time we have. So on Thursday, we'll finish up the chapter with this freezing point depression, boiling point elevation, and some osmosis, and then we'll go back and do more of the math with the solutions and molarity and all that, and maybe practice some more of these as well. So thanks again. I'll see y'all in lab, and then I'll hang around on stream in case there are any questions. So thanks again, chat. Of course, I'll see everybody here in a little bit. Thanks again. And I have the homework printed if you want to grab a copy. On your way out. Yeah, it's just one page this week. See ya.